Hello everyone and welcome to my channel Chemistry by Miss Nidhi Banga. In today's video, I'll be taking the most frequently asked questions from chapter 3 of grade 11, that is classification of elements and periodicity in properties. So let's get started. So our first question is, in which group and period would you place an element with Z equals to 35, that is atomic number 35? To be able to answer this question, you need to know the basic layout of periodic table. You also need to know the method to write electronic configuration. I already have a video on that on my channel. If you do not already know this, please go and check out that video. So let's just write the electronic configuration for the element with atomic number 35. So this is the configuration. I've written this following this method. Now let's see what this electronic configuration can tell us. So we can see that the last electron got filled in P block. So the block is P. Then period number refers to the highest number of n, highest value of n. Highest value of n here is 4. So our period number is 4. Group number. Now we can see that 5 electrons in P block got filled. Okay, 5 electrons in P block got filled. So 1, 2, 3, 4, 5. So this element belongs to the 5th group of P block. But before P block, there are already 12 groups. Okay, so the final group number would be 12 groups before the P block starts, plus the 5th group of the P block, that is 17. So this is how you find out the group number of any element if you can write the electronic configuration. Moving on to the next question. On the basis of quantum numbers, justify that the 6th period of the periodic table should have 32 elements. Okay, so 6th period meaning n equals to 6. If you follow quantum numbers strictly, you'll see that for n equals to 6, L can take value from 0 to n minus 1, that is from 0 to 5. And if we follow that, we can see that L has value 0, 1, 2, 3, 4, 5. This would be S, P, D, F, G and H. So technically till H it can be filled, but the current periodic table that we have has only 118 elements and nothing over F orbital gets filled. So the maximum orbitals that get filled is F. So in 6th period also, only till F orbital it gets filled. So what you have in 6th period is 6s, 6p, 6d and 6f. 2 electrons in 6s, 6 in 6p, 10 in 6d and 14 in 6f. If you add them all, you get the number 32. It shows that in the 6th period, only 32 elements can be placed in the current periodic table. Moving on. The next question is, write the atomic number of the element present in the 3rd period and 17th group of the periodic table. 3rd period, that means n equals to 3, and 17th group. Okay, so 17th group meaning the second last group of the periodic table, right? That means P block. P block and the second last, and in P orbitals we can fill a maximum of 6 electrons, but all P orbitals are not being filled only till 5. So that means it's P5. Okay, 1, 2, 3, 4, 5. And it's the value of n is 3, so it comes out to be 3p5. Okay, now everything before that we can write. So before 3p, we have 1s2, 2s2, 2p6, 3s2, and then we have 3p5 here. So 10 here, till here we get 12, and here we get 17. So the atomic number of the element present in the third period and 17th group is 17. Okay, moving on. Find the total number of electrons in all of the p orbitals of phosphorus. Okay, for phosphorus we know the atomic number, which is 15. So let's write the configuration: 1s2, 2s2, 2p6, 3s2, 3p3. Okay, 3p3. The total number of electrons in all of the p orbitals. So we have 2p6 and 3p3. So the total number of electrons would be 6 plus 3 equals to 9. But what about if you get an element for which you do not know the atomic number? Now let's say you have antimony. Okay, what can help is knowing the mnemonics of the elements placed in a particular group. For example, we know that antimony is placed in nitrogen group, nitrogen family. So we have Nana, Patikar, Asal mein Sabka Bhai hai. This is the mnemonics from which we remember the group members of this group. Now, antimony is here. We know that for nitrogen, it's 2p3. 1s2, 2s2, 2p3, because the atomic number of nitrogen is 7. If nitrogen is 2p3, then phosphorus is 3p3, then arsenic is 4p3, antimony comes out to be 5p3. Now, if it is 5p3, that means all the p orbitals before this are completely filled. That means we have 2p completely filled, 3p completely filled, 4p completely filled, and then finally we have 5p3. Okay, so 6 plus 6 plus 6, 18 plus 3, 21 electrons, p electrons in antimony. Okay, moving on to the next question. Why do elements in the same group have similar physical and chemical properties? Very simple, because they have same number of valence electrons. It is the number of valence electrons that controls the chemical properties. Okay, whether it tends to lose electron or gain electron, whether it tends to form cation or anion, all depends on valence electron. Therefore, it controls the chemical and physical properties of the elements. Moving on to the next question. How do atomic radius vary in a period and in a group? And how do you explain the variation? So, atomic radius down the group increases and along the period decreases. How do we know this? Down the period, we know that an extra shell gets added. Because an extra shell gets added, the outermost electron tends to be farther and farther away from the nucleus as we go down the group. Okay, so since extra shell gets added, obviously as you move down the group, the atom becomes bigger and bigger, right? Along the period, the size decreases because the extra electron, the incoming electron gets added in the same shell. That means the distance from the nucleus doesn't change. The distance from the nucleus remains the same. Okay, so therefore the inner electrons also remain the same. If the number of electrons, inner electrons remains the same, that means the shielding is same. Shielding remains the same. Shielding doesn't change much. But number of protons increases as we move along the period. Atomic number increases, therefore number of protons increases. That means nuclear charge increases. nuclear charge increases and shielding remains the same, that means Z effective, that is the effective nuclear charge, increases. If Z effective increases, that means the outermost electron now feels more and more pull towards the nucleus. So as we move along the period, Z effective increases and the outermost electron feels more and more pull towards the nucleus. That means it gets drawn towards the nucleus or drawn inwards, so the size decreases. Okay, that is how you explain. Basically, you have to tell the ultimate thing that needs to be told is Z effective. Okay, Z effective increases as we go from left to right in a period, and therefore atomic size or atomic radius shrinks. All right, next, explain why cations are smaller and anions are larger in radii than their parent atoms or the neutral atoms. So cations, we know, have protons, more protons than electrons. Therefore, the Z effective would be higher than that of the neutral atom or the parent atom. If Z effective is higher, then obviously the size would be lower than the parent atom. Similarly, you can figure out for anions. In anions, the number of protons is less than the number of electrons. If number of protons is less, nuclear charge is less. That means Z effective is less than the parent atom, than that of the parent atom. And since Z effective is less, size increases. That is why anions would always be bigger than the neutral atom and cations would always be smaller than the neutral atom. The next question from this topic can be asked. You may be given certain ions and you have to find what's common in them. So we can see that in this question, these are the ions that are given: nitride, oxide, fluoride, sodium cation, magnesium cation, and then aluminium cation. So what is common in all of them? Nitrogen, 7 electrons plus 3 more, total number of electrons is 10. Oxygen, 8 electrons plus 2 more, 10. Fluorine, 9 electrons plus 1, 10. Sodium, 11 minus 1, because it's a cation, it has lost 1. So again 10. Similarly, magnesium is also 10 and aluminium is also 10. So they all are isoelectronic species. Okay, so that means they have the same number of electrons. Arrange them in the order of increasing ionic radii, increasing, going from low to high. So if you have isoelectronic species, it's very simple to arrange them in increasing order of their ionic radii. All you have to do is begin with the ion which has the highest positive charge, because that would be smallest. Then go towards and the highest would be, or the biggest ion would be the anion with the highest negative charge. That means nitride would be the largest in size. Now fill up the rest of them. This is what you get. Okay, smallest would be the cation with highest positive charge and largest would be the anion with highest negative charge. Okay, this is how you arrange them in increasing order of ionic radii. If the order asked is decreasing order, then obviously you will have to reverse the order. Okay, moving on to the next question. Okay, energy of an electron in the ground state of the hydrogen atom is minus 2.18 times 10 to the power 18 minus 18 joules. Calculate the ionization enthalpy of the atomic hydrogen in terms of joules per mole. Okay, so now here we have hydrogen atom situation. If this is nucleus, this is the first shell, that is n equals to 1, and the electron is here. So this is the ground state. All right, Then there is another shell n equals to 2, n equals to 3, and it goes on. Now, to be able to answer this question, you need to know what ionization enthalpy is. Ionization enthalpy, also written like this, is the energy required to remove the most loosely bound electron from an isolated gaseous atom. And it's measured in kilojoules or joules, but per mole. For 1 mole of atom, we measure ionization enthalpy. Okay, so in the hydrogen atom, the electron which is in ground state, now when this electron needs to be removed, it needs to go from n equals to 1 to n equals to infinity. That is what it means to completely remove the electron. Now energy for n equals to 1 is given, that is minus 2.18 times 10 raised to the power minus 18 joules. For n equals to 0, the energy for n equals to infinity, that is, the energy is 0. Okay. Now let's see how much energy would be required if the electron needs to go from the ground state all the way to n equals to infinity. So the energy required would be energy of the final state minus energy of the initial state, which is 0 minus 2.18 times 10 raised to the power minus 18 joules. So this comes out to be positive plus 2.18 times 10 raised to the power minus 18 joules. But this is the situation for just one electron. If you need to find ionization enthalpy, that means you need to find this energy for 1 mole of electrons or for 1 mole of atoms which need to lose 1 mole of electrons. So all you have to do is multiply this number with Avogadro number, okay, Na, that is 6.023 times 10 to the power 23. You can do the calculation on your own, and we are moving towards the next question. Would you expect the first ionization enthalpy for 2 isotopes of the same element to be the same or different? Now isotopes. What are isotopes? Isotopes of an element are the types of the element which have same atomic number. That means the same number of protons, and if it's a neutral atom, obviously the same number of electrons, but different mass number. If atomic number is same, that is proton is same, but mass number is different, the only thing that is different in 2 isotopes would be number of neutrons. Okay, this is number and this is neutrons. So only neutrons are different for the 2 isotopes. Number of electrons are same. So ionization energy or enthalpy doesn't have anything to do with the number of neutrons. So obviously it's going to be remaining the same for the 2 isotopes of the same element. Moving on to the next question. What are the factors due to which the ionization enthalpy of the main group elements tends to decrease down a group? So ionization enthalpy, we know, is the energy required to remove the most loosely bound electron in an isolated gaseous atom, measured in kilojoules per mole. Now, the trend that is observed is that ionization enthalpy, shown by any of the 2 ways, decreases down a group and increases along the period. Decreases down the group and increases along the period. In this question, we are asked to only explain why it decreases down the group. So we'll focus on that, but the reverse is true for how it increases along the period. Now, decreases down the group. Basically, it boils down to this. If Z effective increases, ionization energy increases. Because Z effective is what? Z effective is the nuclear pull that the outermost electron feels. If it feels more nuclear pull, then obviously you need to spend more energy to completely remove it, right? So Z effective increases, then ionization energy also increases. We have to keep that in mind. Now the factors that contribute to the trend that we see is first, atomic size. As we move down the group, we know that atomic size increases. If atomic size increases, and why does it increase? Because number of shells keep on adding as we move down the group. If number of shells keep on adding, that means the outermost electron now is farther and farther away from nucleus. Then obviously it will be feeling less nuclear pull, right? So as we go down the group, atomic size increases, therefore Z effective decreases. Okay? Shielding effect. As we go down the group, now we just mentioned number of shells keep on increasing, and in those shells are electrons. If an element has a lot of shells between the nucleus and the outermost electron, that means it has a lot of inner electrons, and those inner electrons are shielding the nuclear charge from the outermost electron. So as the number of shells increases, or as the atomic size increases, shielding effect also tends to increase. When shielding effect increases, that means Z effective finally increases. Z effective would decrease. Okay, that means the outermost electron would now feel very less nuclear pull, so it's going to be very easy to remove it. Okay, so these two factors, shielding effect and atomic size, ultimately contributed to Z effective being very low as we move down the group, and as Z effective decreases, the ionization energy also decreases. Okay, so we proved this. All right, moving on to the next question. The next question is, among the second period elements, the actual ionization enthalpy are in this order. Explain why beryllium has higher ionization energy than boron, and oxygen has lower ionization energy than nitrogen and fluorine. A graph may or may not be given in this question. So now let's see. So as we move along the period, this is lithium going to neon, this is along the period. As we move along the period, we just established that Z effective tends to increase. If Z effective tends to increase, then that means ionization energy also would increase, because now the electrons is feeling more pull towards the nucleus. More pull towards the nucleus, that means it's going to be more difficult to remove that electron, right? So ionization energy increases if the Z effective increases. Okay, now there are two anomalies here, basically just two. Why boron is less than beryllium, and why oxygen is less than nitrogen. So let's see the first case. Beryllium is 1s2 2s2, and boron is 1s2 2s2 2p1. So ionization energy, meaning removing the electron, right, the outermost electron. In beryllium, the outermost electron is in 2s2, and in boron, the outermost electron is in p. Okay, now removing the electron from p orbital is much easier than removing the electron from s orbital. Why is that? Because s orbital is more penetrated into the nucleus. That means it's more closer to the nucleus than p orbital. So if it's more closer to the if it's more closer to the nucleus, then that means the electron in it would be feeling more attraction towards the nucleus, will be more pulled towards the nucleus, then obviously it's going to be more difficult to remove such an electron, right? So removing electron from s orbital is always more difficult than removing electron from p orbital, okay, because s orbital is more penetrated in the nucleus. Now, what happens is, generally students tend to write this, that in beryllium we have fully filled 2s orbital and therefore it's extra stable. So removing electron from fully filled s orbital is going to be difficult. But that concept is completely wrong. Fully filled orbitals or half filled orbitals, this concept only applies when there is more than one orbitals in the subshell. If there are more than one orbitals in the subshell, then only this concept of fully filled orbital and half filled orbital applies. Otherwise, it doesn't. So this concept applies to p orbital, d orbital, f orbital, but not on s orbitals. So please do not write fully filled. If you write fully filled s orbitals, that would be actually wrong. Please don't write that. Write that s orbital is more penetrated into the nucleus. That is why removing electron from s orbital is difficult. Difficult to remove electron. Okay. Moving on to the next case. Oxygen, nitrogen and fluorine. So the ionization energy of fluorine is higher than that of oxygen, and that is fine because that is the trend, because this is the situation of nitrogen, oxygen and fluorine in a period. Okay, going from left to right, Z effective increases and therefore ionization energy increases, and that is why fluorine's ionization energy is going to be higher than that of oxygen's ionization energy. Okay, that is fine. That is what we expect. But how come nitrogen's ionization energy is higher than that of the oxygen? That is because here in nitrogen we have 2p3 electronic configuration, which is half filled p orbitals. And like I said, half filled orbitals impart extra stability. That means it's going to be difficult to remove an electron from half-filled or fully filled orbitals, but only in case of p, d and f orbitals. Okay. So half-filled p orbital in case of nitrogen imparts it extra stability. That is why it's not very eager to lose the electrons. That is why you need to give more energy to remove the electron, and hence ionization energy of nitrogen is higher than that of oxygen. Moving on to the next question. How would you explain the fact that the first ionization enthalpy of sodium is lower than that of magnesium, but its second ionization enthalpy is higher than that of magnesium? Okay, so sodium atomic number 11, and this is the configuration, and magnesium atomic number 12, and this is the configuration. Now, ionization energy, first ionization energy of sodium is obviously lower than that of magnesium, simply because magnesium lies towards the right of sodium in the periodic table, and as we move along the period, because Z effective increases, ionization energy increases. So ionization energy of magnesium, first ionization energy of magnesium is higher than that of sodium, following the simple trend. Okay. Now, why is the anomaly when we talk about the second ionization energy? In second ionization energy, notice that both the atoms have already lost one electron. So now the electronic configuration is this. For sodium ion, after losing one electron, it has achieved the noble gas configuration. And magnesium ion is yet to achieve the noble gas configuration, which it will after losing one more electron, right? So sodium ion is not at all willing to lose another electron and sacrifice its noble gas configuration, but magnesium ion would love to lose this one more electron and attain the noble gas configuration. So magnesium plus is looking forward to losing one more electron and therefore achieving the noble gas configuration, whereas sodium ion does not want to lose any more electron. Therefore sodium ion, or you can say that sodium atom, has a very high second ionization energy, and magnesium has comparatively much lower second ionization energy. Please know that second ionization energy would, for the same element, like comparing only sodium, first ionization energy and second ionization energy, for the same element, the second ionization energy would always be higher than that of the first ionization energy. Okay, let's make that very, very clear. For the same element, the second ionization energy would always be higher than first ionization energy, because after losing one electron, the atom now has become a positive ion. That means Z effective has increased. That is why it's now not that eager to lose one more electron. Okay, more energy needs to be given to pull one more electron from a positive ion, right? So second ionization energy of the same element would always be higher than first ionization energy. But here in this question, we are comparing second ionization energies of sodium and magnesium. I hope that part is very, very clear. Okay, then let's move to the next question. The first ionization energy or enthalpy values of group 13 elements are as follows. Okay, these values are in kilojoules per mole and they are given for the group 13. All right. How would you expand the deviation from general trend? So down the group, what happens? Down the group, ionization energy decreases simply because Z effective decreases, because atomic size increases, more number of shells increases, more number of shells get added. So the outermost electron is farther and farther away from nucleus. It becomes easier and easier to remove it. So less and less energy is required to remove the most loosely bound electron in the atom as we go down the group, right? That is the general trend. And we see that general trend being followed as we go from boron to aluminium, right? Here I've written the outermost configuration for each one of them, okay? And like I said, the trend is being followed going from boron to aluminium. But going from aluminium to gallium, there's a problem. Instead of decreasing, it's increasing just a little bit, but it's still increasing. Now, why is that? Okay, so aluminium is 3p1 and gallium is 4p1. So after aluminium, 3p gets completely filled, and then 4s gets completely filled, and then 3d gets completely filled, and then 4p1 gets filled. Okay, gallium. In gallium, 4p1 is the configuration. That means before that, 10 electrons in 3d orbitals are there. 3d subshell are there. And those 10 electrons, the 3d electrons, are very poor in shielding the nuclear charge. Okay, so nuclear charge is still increasing as you go from boron to aluminium, aluminium to gallium, but the shielding does not increase as much. Why? Because in gallium there are 3D electrons. They are not shielding very nicely the nuclear charge. Therefore, the outermost electron in gallium feels more nuclear pull than it should have, right? So that is why the ionization energy increases instead of decreasing, going from aluminium to gallium. Next, the same trend is followed, gallium to indium, the one that we expected. Going from indium to thallium, there is again an increase, and that increase is attributed to inclusion of 14 4f electron in thallium, which are even worse in shielding, again very, very poor shielding of the nuclear charge. Okay, so these 14 4f electrons are not shielding the nuclear charge as much, and therefore the outermost electron in thallium is feeling a very high nuclear pull, and therefore removing the electron becomes difficult, and therefore there is an increase in ionization energy. Okay, so that explains the two anomalies that we observe, one going from aluminium to gallium and the next one going from indium to thallium. Going from aluminium to gallium, inclusion of d electrons are the reason of the high Z effective, because d electrons are poor in shielding. And then going from indium to thallium, inclusion of 14 4f electrons are the reason why Z effective is unusually high, because because F electrons are also very poor in shielding. So in general, let's write that down. When it comes to shielding, S orbital is the best, followed by P, followed by D, and then the last is F. And D and F are usually considered rather poor in shielding. Okay, so whenever there is inclusion of electrons in D and F orbitals, they are not going to provide as much shielding as was expected. Okay, moving on to the next question. How does the electron gain enthalpy tend to vary along the period and down a group? Okay, so what is an electron? What is electron gain enthalpy? So far we have been doing ionization energy. Electron gain enthalpy is just the opposite. In ionization energy, we wanted to remove the most loosely bound electron. In electron gain enthalpy, we want to add an extra electron in a isolated gaseous atom. Okay. Now, in this isolated gaseous atom, we are adding the electron. So obviously this outermost electron, this incoming electron, needs to feel the nuclear charge, needs to feel the attraction towards the nucleus. So obviously if the Z effective is high, electron gain enthalpy would be high. High meaning more energy would be released. Now, electron gain enthalpy, since the energy is released, we show it with a negative sign. So if, let's say, in an atom, when the extra electron was added to make it an anion, going from X to X negative anion, if the energy that was released was, let's say, 323 kilojoule per mole, this is also measured in kilojoules per mole, then we will show it with a negative sign because the energy was released. So electron gain enthalpy would be written as minus 323 kilojoules per mole. Now this negative sign does not make this value smaller. It only means that the energy is being released. So minus 323 would still be higher than minus, let's say, 280 kilojoules per mole, right? Because here it means 323 kilojoules of energy was being released, and here only 280 kilojoules of energy is being released. Okay, now talking about how it varies along the period and down the group. Now along the period, as we know that Z effective increases, if Z effective increases along the period, obviously electron gain enthalpy is going to be high, but we don't say that. We say that electron gain enthalpy becomes more and more negative, becomes more and more negative. Okay, same way down the group, since Z effective decreases, electron gain enthalpy becomes less and less negative, less and less negative, or you can say more and more positive. Okay, now generally non-metals, because non-metals lie towards the right in a periodic table, they have very high Z effective, they tend to have higher or more negative electron gain enthalpy. So whenever you see values like 300 or minus 200, those values indicate that it's a non-metal. When we talk about metals, metals obviously would have the opposite trend. There will be less and less, very less value of electron gain enthalpy. So you would see values along the lines of minus 40, minus 60, minus 70, yet a negative value. Okay, less negative value, less negative electron gain enthalpy for metals. Noble gases. Now, since noble gases are not at all interested in accepting any electrons, they tend to have a very high value of electron gain enthalpy, meaning energy actually doesn't get released, it needs to be provided. In a way, we are saying that electron is being forced onto the noble gas atom, right? Since electron is being forced, energy needs to be provided, and that is why noble gases tend to have positive electron gain enthalpy. Okay, nitrogen, although it's an non-metal, nitrogen also tends to have a positive electron gain enthalpy. The positive number is not very high, it's merely plus 7 kilojoules per mole, but still it's positive. Now, why is it positive? Why, even after being a non-metal, it's reluctant to accept electron? That is only because nitrogen has a very stable configuration. It's happy with its configuration. Adding any more electron is going to disrupt the stable arrangement that was 2p3. Okay, that is why the nitrogen atom is rather a little reluctant in accepting the electron. Okay, so now I think I've answered this question. How does electron gain enthalpy tend to vary along a period and down a group? Okay, moving on to the next question. Which of the following pairs of elements would have a more negative electron gain enthalpy? Oxygen or fluorine? Now, oxygen lies onto the left of fluorine. Okay, fluorine lies onto the right of oxygen. So along the period, we know that Z effective increases, therefore electron gain enthalpy would be more negative going from left to right. More negative going from left to right. So fluorine will have a more negative electron gain enthalpy out of oxygen and fluorine. Talking about fluorine and chlorine. Now here there is an exception. Fluorine is above chlorine in a group. Okay, so you would expect that down the group, since Z effective decreases, the value should be less negative for a chlorine atom, but actually it's more negative for chlorine atom. Chlorine atom has a more negative electron gain enthalpy. Now, why is that the case? That is the case because fluorine has configuration 1s2, 2s2, 2p5. Chlorine, it's 3p5. I'm not writing the configuration before 3p5 because that is what it matters. So in fluorine, the extra electron enters in 2p subshell. In chlorine, the extra electron enters 3p. Now there are already 5 electrons present in 2p and 3p. But 2p, since it's smaller, 2p is smaller, 5 electrons present in a smaller area are going to repel or not very easily accept the incoming electron. Okay, so the 5 electrons present in smaller 2p orbitals gives or repels the incoming electron. Okay, whereas in case of chlorine, the incoming electron does not face as much repulsion because there are 5 electrons present but in a larger 3p orbitals. We know that as value of n increases, the size also increases. So 3p is definitely bigger than 2p. Okay. Moving on to the next question. Would you expect the second electron gain enthalpy of oxygen as more positive, more negative, or less negative than the first? Justify your answer. The second electron gain enthalpy of any element is always going to be positive. Why? Because when an isolated gaseous atom accepts an electron, it becomes a negative ion, that is an anion. Now this anion has obviously more electrons than protons. So the next electron that needs to be added here is going to feel a lot of repulsion from already present more number of electrons, right? So this electron, the second electron, is in a way going to be forced upon an already negative ion, right? So your second electron gain enthalpy is always going to be positive. That means energy needs to be given. Energy needs to be given. Needs to be given to add one more electron to an already negative ion. Moving on to the next question. Okay. So first ionization energy, second ionization energy, and electron gain enthalpy for the few elements are given. These values are given. We have to answer these questions based on the data provided. Okay. Now let's first look at the data and find out if we can classify these elements as metals, nonmetals, and noble gases. So I told you before that noble gases tend to have a positive electron gain enthalpy. That means they are very, very reluctant to accept an electron, and obviously because they are noble gases, they are very stable. They also tend to have very high ionization energies. So which element fulfills the criteria? Fifth element has very high ionization energies and also a positive electron gain enthalpy. That means this has to be a noble gas. Okay. The first element has very low first ionization energy, very high second ionization energy, and a small negative value of electron gain enthalpy. That means this has to be a metal. Metals generally have low ionization energies and very low negative value of electron gain enthalpies. Okay. Same is the case for the second element. So this is also going to be a metal. The next two elements, they have rather high negative value of electron gain enthalpy. That means they have to be non-metals. Okay. Talking about sixth one has to be a metal. So now that we have classified these elements as metals, non-metals and noble gases, let's answer rest of the questions. Okay. So the first question is the least reactive element. It says element, that means it can be a noble gas as well. And we know that noble gases are least reactive, so it's an easy answer that element 5 or fifth element is the least reactive element. Moving on, the most reactive metal. Most reactive metal would be the one which has, first of all, we have these three choices only, 1, 2 and 6. The most reactive one would be the one which has very low first ionization energy and also very low second ionization energy. So element 2 fills the criteria. See, element number 1 has very high second ionization energy, right? So this does not fulfill the criteria. So most reactive metal would be element number 2. Okay. Third is the most reactive non-metal. Of the two non-metals, element number 3 has highly negative electron gain enthalpy. That means a lot of energy is released when this accepts an electron. That means it is very reactive. So again, element number 3. Least reactive non-metal, we have only two non-metals. If this is more reactive, then this is going to be less reactive. Okay, so 4. Now, the metal which can form a stable binary halide of the formula mx2. Stable binary halide, if this is, the formula is mx2, X we know, halides we know have the charge -1. That means the metal has to have a +2 charge. Okay, +2 charge meaning it must be willing to lose 2 electrons. That means it has to have a rather low second ionization energy. And we can see that from this, and this, the element 6 has considerably low second ionization energy. That means element 6 is willing to lose 2 electrons and form a divalent ion and therefore form mx2. The metal which can form predominantly stable covalent halide in the form of mx. So that means this is the metal which has to have +1 charge. That means it must be willing to lose just 1 electron but not the second electron. And covalent, that means it can have high ionization energy as well. So our answer is first. Okay, because it has, the first element has very high second ionization energy. That means it's not at all willing to lose 1 more electron. It would lose only 1 electron, right? So 6th is the answer for the 6th question. Okay. Oh, sorry, my mistake. First element. Okay, this first element would be the answer to the 6th question. Okay, all right, moving on. Nitrogen has a positive electron gain enthalpy, whereas oxygen has negative. Explain. Oxygen, however, oxygen has lower ionization enthalpy than nitrogen. So, nitrogen, the electronic configuration is 1s2, 2s2, 2p3. Oxygen, the electronic configuration is this. Okay, out of the two, nitrogen has a very stable electronic configuration because it has half filled p orbital. Now this configuration is very stable. That means nitrogen is neither willing to lose electron or gain electron. That's why it has a higher ionization energy than oxygen, and also its electron gain enthalpy would be less negative or more positive. Okay, so nitrogen also has a positive electron gain enthalpy. Positive electron gain enthalpy, and ionization energy is also higher than that of oxygen because nitrogen is neither willing to lose electron or gain electron owing to its extra stable electronic configuration, which is half-filled p orbital. Moving on, how does the metallic and non-metallic character vary on moving from left to right in a period? So what is metallic character? Metallic character is the tendency of an element to lose electrons. Tendency to lose electron. If the element is willing to lose electron, it has metallic character. So, along the period, Z effective increases. If Z effective increases, the element would not be able to or would not be willing to lose electrons because electrons would be tightly held. So along the period, metallic character MC decreases, and that is also proven by the fact that in the periodic table onto the right we have only non-metals, right? Because metallic character decreases along the period. Down a group, Z effective decreases because then its extra shell gets added, therefore metallic character increases. So in a group, as we go from, especially this is seen in P block, you will see that for some groups, on top there would be non-metal, then somewhere in the middle of the group there would be metalloids or semi-metals. Towards the end of the group you would see metals. That means that proves that metallic character increases down a group. The opposite is true for non-metallic character. Non-metallic character is tendency to accept electrons. So again, Z effective needs to be high to be able to accept electron. Along the period, since Z effective increases, non-metallic character also increases. Similarly, down a group, Z effective decreases. Therefore, non-metallic character decreases. Okay, moving on. Which of the following oxides is least acidic? Before we solve this question, let's talk about oxides in general. Now, metal oxides, they are generally basic in nature. Okay, and as metallic character changes, the basicity of the oxides will also change. So along a period, metallic character decreases, so basicity of the oxide would also decrease. Okay, non-metallic oxides are acidic in nature. Again, as the non-metallic character changes along the period or down the group, similarly on the same lines, the acidic character of their oxides would also change. Talking about amphoteric oxides. Amphoteric oxides are the ones which react with both acids and bases to give salt and water. Salt and water. Okay, so ampho means both. If an oxide reacts with both acids and bases to give salt and water, that would be called as amphoteric oxides. And we have two of this category. Amphoteric oxides are zinc oxide, amphoteric oxides. We have zinc oxide, which is amphoteric, and we also have aluminium oxide, which is amphoteric. That means these two oxides react with acids and bases both to give salt and water. Reactions we have done in grade 10. Neutral oxides are the ones which react with neither acid or nor base. They don't react with any of them. Okay, so they don't react with any of them to give salt and water, so they are called as neutral oxides. Example of neutral oxide would be water, carbon monoxide, and nitrogen, lower oxides of nitrogen, that is NO or NO2 also. No, not NO2, N2O. Okay. So any metallic oxide like sodium oxide, magnesium oxide, calcium oxides, they tend to be basic. That means they would react with acids to give salt and water. Non-metallic oxides such as carbon dioxide, sulfur dioxide, sulfur trioxide, nitrogen, higher oxides of nitrogen such as NO2, NO3, they would be acidic oxides. That means they would react with base to give salt and water. Okay, now this is what I just explained, how their character changes along the period and down the group. Now, when we compare oxides of the same element, it is seen that lower oxides tend to be less acidic than higher oxide. In some cases, it can higher oxide would be acidic and lower oxide can even be neutral, or in some cases, it can even be basic. Okay, so here there are some examples. Let's compare their acidity. So carbon monoxide, carbon dioxide. Carbon dioxide is obviously the higher oxide, so it will have higher acidity. And we know that carbon dioxide is acidic. Carbon monoxide, on the other hand, is neutral. Similarly, N2O and NO2. NO2 is acidic, and this is again neutral. Comparing SO2 and SO3, SO3 is more acidic than SO2, although they are both acidic. Okay, less acidic and more acidic. Okay, now coming back to the question, which of the following oxide is least acidic? Now, phosphorus and arsenic, these are the two elements in the four options. Arsenic is below phosphorus in the group, right? And down the group, we know that what happens down the group? Down the group, metallic character increases, therefore basic character increases, therefore acidic character decreases. Down the group, acidic character or acidic character of the oxide would decrease. Okay, so arsenic's oxide would be less acidic than phosphorus oxide. That means these two can be ruled out as the answers. Talking about arsenic oxides, we can see that this is a higher oxide and this is a lower oxide. Okay, lower oxide tends to be less acidic. So out of the two, this one would be less acidic. So clearly our option is this, AS4O6. Moving on to the next question. Prove the basic nature of magnesium oxide. There could be any oxide, any basic oxide, not just magnesium oxide. So whenever you have to prove the basic nature of any oxide, all you have to do is take that oxide and make it react with an acid and show the product. In the product, you have to show salt and water. So magnesium oxide plus acid, let's take any acid, let's take HCl. The salt that would be formed is MgCl2 and water. Balance the reaction and you have shown it. Another way to show is that take the oxide and make it react with water and form the hydroxide. Okay, we know that metal hydroxides are alkalis, so this also proves that the magnesium or the metal oxide, any metal oxide, are basic in nature. Similarly, when you have to prove the acidic nature of any oxide, you take the oxide and make it react with a base. And in the product, you show that a salt is formed and water is formed. Okay, so let's say SO2 and let's make it react with a base. Actually, this could be a little confusing because you may not know the formula for the salt that is formed. In that case, so what you do is take the oxide and make it react with water and show the formation of acid. So SO2 here combines with water to give you what? H2SO3, and this is sulfurous acid. Sulfurous acid. Okay, this is how you show the acidic nature of any oxide. Now, next question. Compound between oxygen and fluorine would be called what? The confusion here is, would it be called as oxygen fluoride or fluorooxide? Fluorooxide. It would be called as oxygen fluoride because out of oxygen and fluorine, fluorine is more electronegative and therefore will assume the role of the anion. And we know that in a compound, anion is the one that gets the suffix. The suffix here is "ide." That means fluorine is acting as the anion, and that is because fluorine is more electronegative. Okay. Moving on. What is the basic difference between the terms electron gain enthalpy and electronegativity? So, electron gain enthalpy and electronegativity, these terms can be confusing because both talk about tendency to attract electron. Okay, but there are some differences. Electron gain enthalpy is the energy released when an isolated gaseous atom accepts an electron. Okay, so here complete acceptance of electrons take place. An atom becomes ion. Okay, and some energy is released. But when we talk about electronegativity, it's only a tendency of an atom to attract a shared pair of electron in a compound. So if you have X and Y, first of all, in electron gain enthalpy, we were talking about isolated gaseous atom, one atom. Okay, and here in electronegativity, we are talking about a compound which are sharing, and in the compound, the two atoms are sharing electrons, and the more electronegative element would attract the shared pair of electron towards itself. So that means Y is more electronegative. Okay, so here first of all we are not talking about isolated atom, we are talking about a compound. Then the complete transfer of electron doesn't take place. Electrons are merely shifted to a more electronegative element. Okay, and it's a pair of electron that gets shifted. But main thing to notice is it's only a tendency. It doesn't have an absolute value. Electron gain enthalpy can be measured. It has an absolute value, which is followed by a unit, okay, which is kilojoules per mole, whereas electronegativity cannot be measured. The values that, the electronegativity values that are given to different elements, they are just given based on the tendency. The random values are given, not random, I mean the values are given based on their tendencies. They are given by the scientist. They are assigned by the scientists. Okay, we did not measure it by some method. Okay, now since it's only a tendency, it doesn't have a unit. It's a unitless property. Moving on to the next question. Okay, so the last question of the video is that the first member of each group of representative elements, that is S block and P block elements, shows anomalous behavior. Illustrate with two examples. So here, when we talk about first member of each group, that means S and P, we are talking about second period elements. Okay, second period elements as in lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and such. Okay, they show anomalous behavior, different behavior than the rest of their group members. First of all, because they are in the top of their group, and we know that as we go down a group, size increases considerably. So that means the first member is going to be very small. If it's small, its Z effective would be higher. That means its electronegativity would be higher compared to the rest of the members. Therefore, its tendency to form covalent compounds would be higher. Okay, rather than losing electron, it would form covalent compounds. It would prefer to share electrons. This is for metals. Then another thing about the first member is that they tend to resemble more to the diagonally opposite element rather than the member of their own group. So lithium resembles more with magnesium, which is diagonally opposite to it, and similarly beryllium resembles more to aluminium, which is also placed diagonally opposite to beryllium. Now why is that? That is because, as you know, when we go from left to right, size decreases, but then when we go, I'll use a different pen here, when we go down the group, size increases. So size is decreasing here and increasing here, so basically doesn't change much. Okay, so lithium and magnesium's size is almost the same, whereas lithium and sodium's size would be very different. Sodium is much bigger than lithium. Magnesium is still bigger than lithium, but charge on magnesium is also higher than charge on lithium, and this results in similar charge by size ratio. So magnesium has higher charge than lithium, but also higher size than lithium. So ratio of charge by size of magnesium is very similar to that of lithium, and therefore they resemble each other quite a lot when it comes to chemical properties. Same is the reason for showing similar chemical properties of beryllium and aluminium. They're also very similar for the same reason that they have very similar charge by size ratio. Okay, next is that the second period elements do not have d orbitals. If they do not have d orbitals, that means they cannot make more than 4 bonds. The maximum number of bonds that they can form is 4. How? Because they have only one s and 3 p in the outermost 3 p orbitals in the outermost shell. So only 4 orbitals that can occupy a maximum of 4 pair of electrons. That means a maximum 4 bonds can be formed for members of second period. Okay, whereas rest of the group members, third period members or fourth period members, they can make more than 4 bonds because they can keep some of the electrons in d orbitals as well. They have d orbitals available to them. Okay, but for second period, because n is equal to 2, you can have a maximum of 2s and 2p. 2d is not there. Since 2d is not there, you can have a maximum of 4 bonds, right? Then they also have the ability to form p pi bonds with themselves or with other elements of the same period, and that is attributed to their small size. Because they are smaller in size, they can actually come very close comfortably and have a sideways overlap to form pi bonds, right? That is why they can form multiple bonds amongst the member of their own period, of the same period. Okay, that is all for today. That ends with this video, and I hope you liked the video. I hope it helped, and if it did, please subscribe, share and like. Thank you.